In this video, I'm going to explain what is meant by a renewal model, and I'm going to explain why they're useful in epidemiology. So to start, I've just written down the typical renewal equation as we encounter it in epidemiology. And don't worry if any of these terms seem unfamiliar to you, we're going to explain what they mean through the course of this video. And in this video, we're going to contrast them first of all with a very different approach to modelling, which is used in epidemiology, which is so-called compartmental models. We're then going to talk about the intuition behind how the renewal model works, and then finally we're going to explain how the renewal model allows us to quite straightforwardly estimate the instantaneous reproduction number, RT, which is really important for trying to understand whether or not there have been changes in transmission throughout the course of an epidemic. So let's first of all start with compartmental models. And one of the simplest compartmental models is a so-called SIR model. And what that means is that we put individuals into different compartments. An S compartment standing for susceptible individuals, an I compartment standing for infected and infectious individuals, and another compartment R standing for recovered individuals. And by assuming that we've got individuals and we put them into three compartments, implicitly what we are assuming is that there are no other factors that affect the transmission of disease within this population. So for example, we've not accounted for things like age or other sort of differences, geographical differences for instance. Here we're just assuming that whether an individual is susceptible, infectious or recovered are the only things that matter. And there are rates at which individuals transition between these compartments. So a susceptible individual can come into contact with infectious individuals and then themselves become infectious, and over time infectious individuals can recover. And so in these types of models we've got to make assumptions about the rates at which these transitions occur, and it's often the case that we say that the rate at which a susceptible individual becomes infectious is given by some parameter, let's say beta, times the number of infected individuals. So here I'm implicitly assuming that the population is well mixed, for example, and there is a rate at which infectious individuals recover, and we might call that gamma, for instance. So I've had to make a host of assumptions here in order to understand the sort of model structure, and to be able to solve this model I actually need to make three more assumptions. I need to assume the number of susceptibles at some point in time. Here I'm going to assume that that's at time 0 at the start of the epidemic. Also the number of infectious individuals at time 0, call it I0, and the number of recovered individuals at time 0, which I call R0. And the power of these types of model is that given my assumptions, I can sort of simulate what might happen over the course of an epidemic. So here I'm going to just denote time here on the bottom axis, and my vertical axis here is going to be the number of individuals belonging to each of these three different compartments. And I'm going to draw a sort of typical sort of pattern that you might get in the course of an epidemic. So this blue here might be the number of infectious individuals over time. The number of susceptible individuals declines over time. So it looks something like that. And finally, number of recovered individuals grows over time and might look something like this. So this is a very just sort of illustrative example of what the solutions to this model might look like over time. And implicitly here I'm assuming that our sort of compartmental model here is a deterministic model, and so we've got sort of smooth lines that I'm drawing here over time, and there's only one possible solution. So these models are really, really powerful. What they say is, given a host of assumptions, we can then ask sort of what if questions. In other words, we can investigate different types of scenarios. For example, investigate different types of interventions that could be brought in to affect the course of disease transmission. But when we come to actually use such models to investigate what is going to be the outcome of a disease invading a population, we need to make a host of assumptions, and those assumptions attempt to in some way, so-called mechanistically, capture the transmission path. In other words, we're trying to model the individual mechanisms by which a pathogen is spread between individuals. And so if some of our assumptions are wrong, then we might not make very good predictions about what's going to happen. And for instance, in COVID-19, we would need a model that was far more complicated than this simple SIR model to be able to adequately describe transmission. For example, we might want to include a model which had an S compartment, and then there was a so-called pre-symptomatic compartment and a asymptomatic compartment, and then there's an infectious compartment and a recovered compartment. So we've got a few more different compartments here, and I'll explain what those mean in just a second. So susceptible individuals, when they come into contact with infectious individuals, they can either go down a path whereby they become pre-symptomatic, which means that they're ultimately going to go on to be symptomatic and infectious, or susceptible individuals can go and they can become asymptomatic, which means that they don't show any symptoms, but they can still be infectious. And those asymptomatic individuals can recover at some rate, and the infectious individuals can recover at some rate. In COVID-19, unfortunately, it's the case that recovered individuals lose immunity over time. So we know that recovered individuals become susceptible again at some point. So this is still a really, really simple model of how COVID-19 might work. But notice that I've had to introduce lots more different assumptions into this model. And with each of these arrows and with each of the compartments, I will need to make one more assumption. So notice that particularly early on, when we've got a new pathogen that is invading a population, we may not be very confident about these various assumptions that we're making. And so these models, whilst they're great, require us to know quite a lot about the pathogen that's spreading in the population. And if we get any of those things wrong, it's possible that our model can lead to misleading predictions about what's going to happen in the future. So now I want to talk about another modelling framework, which requires us to make fewer assumptions. And that modelling framework that I'm going to talk about now is that of renewal models. And these are a very different type of model. They're, rather than being mechanistic, they're statistical in nature. And as I say, they are generally far simpler than compartmental models. And to illustrate how these models work, I want to think about a really simple example, where we imagine we are looking into the past, and where we imagine that there were no previous infections on one day ago, there were no previous infections 2 days ago, and there were 5 infections which occurred 3 days ago. And let's say there are no more at any other sort of times further back into the future, 4 days in the past, and so on. So our question we want to ask in renewal models is, given this history of infection, how many infections would we expect to occur today? And to be able to answer that question, effectively what we need to know is, how does infectiousness vary over time since a person becomes infected? And that generally depends on a few different things. It depends on the pathogen load within the individual, so how many pathogens are there in that individual, and the rate at which those pathogens are shed and so can infect other individuals. And it also depends on other things, such as the contact rate between infected and susceptible individuals. And there are potentially other factors that could also affect infectiousness too. But the idea with renewal models is that we can sort of think about infectiousness as a whole as varying as a function of time since an individual was actually infected. And I call that quantity tau. And we can draw a probability distribution which governs effectively the amount of time which elapses between a first person becoming infected and subsequent individuals becoming infected by that individual. And the sort of profile that this represents is kind of intuitive. When individuals first become infected, so that's sort of the initial phase, then they're not very infectious because the pathogen hasn't multiplied sufficiently within the body, and it hasn't started to be shed in any great number from that body either. Then there is a period where individuals are highly infectious, and then there is a subsequent period when that individual perhaps clears the pathogen from their body and their infectiousness effectively goes to zero eventually. And the renewal equation which we wrote down was a discrete renewal equation which effectively discretized everything by day And so I'm actually going to go ahead and I'm going to discretize this probability distribution. Okay, so I've gone ahead and I've discretized that probability distribution, and each of these bins just represents the probability that a secondary infection will occur on that day. So the area technically underneath this bin here on day 5 gives us the probability that a secondary infection will occur 5 days after an individual is infected. So this distribution that I've drawn down here is what is known as the generation time distribution, because effectively it governs or describes the typical time that elapses between generations of infections. And it turns out that in order to know the number of infections that we'd expect to happen today, we need to know the generation time distribution, and we need to know something about the intensity of infectiousness. And the intensity of infectiousness is described by the reproduction number, RT, or technically the instantaneous reproduction number. And the instantaneous reproduction number effectively accounts for lots of different factors. So for example, it accounts for the number of susceptible individuals that are left in the population. And it also accounts for effectively if there are changes in, let's say, the contact rates within a population. In other words, individuals, for example, are not moving as much or going out of their homes as much, and so they're less likely to come in contact with others. That sort of type of situation would be described by changes in the instantaneous reproduction number. And the instantaneous reproduction number represents effectively the average number of infections which a primary infection would generate throughout the course of their infection. And technically I need another assumption on top of that, and that second assumption is assuming that the conditions in the population remain the same. But I don't want to get too stressed out by that second condition now. You can just think about these two things as being what's important for determining the number of cases today. The typical time which elapses between infections and the intensity of infections, which is represented by RT. And when I have both of those things, I can then predict what the average number of infections is today at time t. So if we go back to our slightly idealized example up here, we can sort of think about, using these concepts I've just introduced, how many new infections do we expect to happen today? And so I can write the expected number of infections occurring today at time t, or time 0 if I want to look up at that diagram here, and that's just equal to RT times the probability that 3 days elapses between cases. And I haven't written it here, but I'm actually going to call each of these respective probabilities omega of tau. So omega 3 is the probability that 3 days elapses between subsequent infections, times the number of infections which occurred 3 days ago. So that's the number of infections at time t minus 3. And in that case, this is just 5. Okay, so let's break that down. So we've got 5 individuals who were infected 3 days ago, and then we've got the probability that 3 days elapses between a primary case and a secondary case, and we've got the number of infections which that individual tends to generate throughout the course of their lifetime. Okay, so in this example, all we've done is we've taken our infection count 3 days ago, we've multiplied it by RT and by omega 3, and we can think about what would happen if I had a more general history of infections. For example, if I had sort of 1 infection, let's say 1 day ago, and 2 infections 2 days ago, and so on. Well, all I would need to do then to extend my model is I would just write RT times omega 1 times I t minus 1. So that's the number of infections which began 1 day ago, times the probability that 1 day elapses between their infection and then causing subsequent infections, plus omega 2 times I t minus 2. So now we're considering infections which began 2 days ago, plus omega 3 times I t minus 3, and so on, all the way up to infinity. And I can abbreviate this whole thing on the right hand side here by a much simpler notation, which is that it's equal to RT times the sum from tau equals 1 to infinity of omega tau times I of t minus tau. Okay, and so now we've actually derived our renewal equation which we began with at the start. Okay, so now we've gone ahead and we've derived the renewal equation. And we noticed that whilst I had to make assumptions on the relative strength of transmission and also the time which typically elapses between subsequent infections, I didn't actually have to make all that many further assumptions about what was going on. And that's the real benefit of renewal models. They're much simpler than compartmental models in general. And that simplicity is really a benefit in some ways because it means that there's less we can get wrong. And there being less that we can get wrong is really particularly advantageous when we want to estimate quantities of interest. So when we want to take some real data that has come out, for example, during an epidemic, and we want to then use that data to inform our model, and in particular to estimate things that we're interested in. And something that we're pretty much always interested in estimating is the reproduction number. And if you want to estimate the reproduction number, then compartmental models can be used for that purpose. But bear in mind that compartmental models require us to make lots of assumptions. And if any of those assumptions are wrong, then we may get bias in our estimate of the reproduction number. Whereas the renewal equation that I've written down here suggests a much simpler approach to estimating the reproduction number. All I can do is I can rearrange this so I have RT is equal to the expected number of infections today divided through by the sum from tau equals 1 to infinity of omega tau I t minus tau. So we now have nearly everything we need to be able to find an estimate of RT. This bottom here just depends on the history of infections and the so-called generation time distribution, which we typically can get from other studies, or actually what we end up doing a lot of the time is we replace this with the serial interval distribution, which is simpler to estimate because the serial interval is the time which elapses between individuals becoming symptomatic and their offspring cases becoming symptomatic, which is simpler to estimate because we can observe when individuals become symptomatic. That's the definition of what it means to be symptomatic, whereas it's more difficult to know when individuals were actually infected. And often what we do actually as well, I should say, is we actually use as our history, we don't use the history of infections, we end up using the history of cases. So in other words, when individuals became symptomatic. But this numerator here is still a bit problematic because I've got this expectation term here. But if I want to just get an estimator, then what I can do is I can just say, well, actually we observed a given number of cases today, and that number of cases was IT, and then I effectively use that as my estimator of the expectation. So I just have on my numerator here the true number of disease cases which occurred today. And so this provides us with a really simple estimator of the instantaneous reproduction number, which is typically quite robust because I've had to make fairly few assumptions to arrive at it. In reality, the way in which we estimate the reproduction number is a little bit more complicated than what I've illustrated here, but nonetheless you can see that using the renewal equation allows us to get at this quantity quite quickly, whereas I haven't gone into the detail at all, but in compartmental models it's much more complex and I need to make far more assumptions about a situation.